Hi everyone again. This lecture we will try to cover the VCO, which is also sometimes called as the voltage controlled oscillator. This is one of the key blocks that is in the frequency synthesizers on chip. We have to generate a certain frequency. So as we have seen in the previous lectures on the receiver architecture, you're trying to receive at certain frequencies. So at the mixer you have to generate certain frequencies, which we call as LO. So LO for like local oscillator. So how do we generate it? They actually are generated on chip from blocks which are called frequency synthesizers, and a key part of that is the VCO. So we'll try to focus on that in the next few pages that we have that I go through. So first of all, I'm trying to show a block diagram of what I'm used to calling it as a frequency synthesizer. It also has the name called PLL. PLL is for phase locked loops, and maybe there are some other names. I'm showing this to give you a high-level idea of what are the different blocks, how do we generate this frequency, how these different frequencies are synthesized. But at the end, this lecture is not going to be dealing with a lot of these blocks. We will only focus on the block which I just want to share here as one of the key blocks, which is the VCO, my personal experience with designing VCOs and what are the key things to talk about, look for. You all have seen different architectures and a lot of information in the textbook. This is a carryover to what else I learned in the industry, and if you go to the industry, what all you might be looking for. So here is a PLL block diagram. We start from here, which is called FREF. FREF is a reference frequency. It mostly comes from a crystal oscillator. This is a very accurate frequency reference, which is off chip, and that is has extremely high accuracy. So you can only generate an accurate clock, which is our output here. This is the frequency we're trying to generate as, say, the VCO output. You have to have some sort of an accurate input, right? And that input is this. So from the crystal oscillator being accurate, we are trying to generate an accurate output here. So what are the other different things for the blocks in the PLL? So we have the phase frequency detector, which is called PFD. Sometimes it could just be a phase detector. So but here let's just go with the traditional block diagram of what you must have seen. So I kept it same as it's in the textbooks or on different kinds of publications. Phase frequency detector, CP is for charge pump. We have a loop filter after that. That loop filter generates a voltage called V-tune. This is the tuning voltage for the VCO. So remember, this is a voltage control. So by changing this voltage, we will change its output frequency. So this block, its output is frequency, its input is a voltage. Okay, and the output is a kind of a sine wave whose frequency can be changed by changing this V-tune. So you take the output of the VCO again, you divide it by some value n. It could be an integer value or it could be a fractional value. And as you divide it by n, right, you bring it in such that whatever your FREF is, FREF times n will be actually your VCO frequency. That's what this loop is trying to do. This is a negative feedback loop. Well, when implemented properly, and again, as I mentioned, we are not getting into too much details of these blocks, but I'm taking the generic block diagram, and what this would do is it would generate a VCO output frequency will be n times FREF. That is what this guy is trying to compare, and he's going to make these two frequencies equal. Okay, so this is a traditional PLL that you might have seen in many places. As I mentioned, we will only focus on this VCO block. To be specific, we will look at LC VCOs. There are broadly two different kinds of oscillators which are used in most of the chips. The majority of being based on the LC tank oscillators, and the other category is ring oscillators. You could also do a series of cascaded inverters, simple inverters, and if you feed them back, they will also start to oscillate when they satisfy the criteria for oscillation, and those are called ring oscillators. They are used in many applications where the noise, there is a specification as we will cover later on called phase noise. If the phase noise is not so hard, it's relaxed, you can use ring oscillators in those applications. But in most of the cellular, Wi-Fi and various kinds of these applications, you actually have got some stringent phase noise requirements. You want a very clean oscillator. That's what it means. If the noise is less in the oscillator, means it's very clean, you actually tend to go with LC oscillators. So here we'll cover the LC VCOs. So let's go for looking at what is the basic fundamental. You already know it, but I'll try to repeat it again. So what we have is we start with an LC tank. There is an L and a C. If we had a tank like this, we know that, and somehow if this tank oscillated, let's say everything here, we somehow were able to inject an energy into this tank and there were no losses, then it will start oscillating. And what would be the frequency of oscillation? Omega oscillation is 1 over square root of LC. That is how it would oscillate. By magically, if we could inject some energy into this and everything was lossless. But in reality, what happens is, these inductors, which we make on-chip inductors, they have finite losses with them. The series resistance is given as RS, and what you can show the RS is roughly, we represent this way by a Q, Q being the quality factor of the coil. These Q numbers could be, typically you could get 10, 12, 15 maybe as the Q numbers. But if you had really good thick metal in the IC technology, as you go to the topmost metals, the metals get thick. If you have more and more thick metal, you could even approach maybe 20, 25 type of Qs. The bottom line is the Q is higher, this loss is lower. But this is a simple way you can represent the loss, RS, which will be L omega, which is the impedance of this, the reactance part of this impedance here of the whole thing, divided by Q. So higher the Q, better is the lower are the losses, better is going to be this oscillator. Okay, so since we have losses, even if I injected some energy into this LC tank, what it would do is it would try to oscillate, but then it will damp down, exponentially because of this lossy component. It will not be able to sustain those oscillations. It will start oscillating and then it will just die out. One way of taking, you could take this series loss and you can actually go to this one and convert it into a parallel equivalent resistor. So you have the same LC tank and all the series losses you had of the inductor, you can convert it with an equivalent RP, equivalent parallel resistance, which could be given roughly as Q times L omega at the oscillation frequency. Again, this transformation is not valid for the whole range of omegas. It is only valid when Q is high. Okay, and Q is high, so we will only focus this to omega oscillation, where we have the best Q. Let's say we have the inductor, and we can then represent it only for this narrow band of frequencies around the oscillation frequency. We can say RP is roughly Q times L omega. Okay, so this becomes the lossy part. So now we have a lossless part and we have a lossy part, and to actually, and again, as I mentioned, if I injected energy into the system and let it go, it will not oscillate because these losses will kill down the oscillations. So what we need here is, in parallel with RP, we need some sort of a negative resistance. We have an RP, the lossy part. If we could somehow generate a negative resistance which will cancel this, okay, RP and this minus R, if the effective resistance of this, we could make it very large, almost infinite, okay, or even negative, then what will happen is if we inject the energy here, it will start oscillating and it will keep on oscillating. That is the basic principle of these LC oscillators, where we have an LC tank and we try to overcome the losses of the LC tank, the losses primarily because of the inductor, by a negative resistance. I say it's primarily because of the inductor because in this model I've only showed the inductor to be lossy, the capacitor is not. But as we will go forward and look at it, you will see even the capacitors could start getting lossy based on how we implement them, and they would also determine the Q. They will also have lossy elements and they will also determine the overall Q of this tank. So we will look at that later, but for now let's just keep the model simple to give you the idea of what I'm talking about. Oops, this becomes too big, but maybe it's, oh, this is too small, big. Okay, let's just go ahead and go through the lectures this way. We'll have 2 pages, and hopefully in the video these pages show up okay, not too small. Okay, So let's say, how are we going to generate this negative resistance? We said that we have some losses and we want to generate this negative resistance, right? So here is a simple circuitry that we mostly use, and we end up calling it as the VCOs core. Core means where we are trying to generate the negative resistance. So let's have two cross-coupled NMOS devices like this. Okay, and if I wanted to know what is the impedance looking up here, how does it generate? I'm saying this is a negative resistance. Let's see how does it generate a negative resistance. You can put a superficial voltage source Vx and try to say, if this is Vx, this is Ix going this way. Let me see what kind of a V by I do I get, Vx by Ix. And if you work it out, you will see that in this configuration, the I will actually not go this way. It will actually end up going this way. Because see, this positive, right, Vx, we are considering this node to be positive. This is applied here, which means this is the gate voltage here roughly, right? And that is going to pull the current this way rather than this way. So when you do the current and you look at what is the V by I, you will see that this will come to 2 over Gm. One of the ways to simply do it would be, you can take this Vx, and I didn't draw it, I should have, is break it into two voltage sources. Here have a voltage source called Vx by 2 and another one called minus Vx by 2. So you can break this Vx into two of them and put a ground in the middle. So if you put a ground in the middle, the total series voltage will still be Vx, but each will get either Vx by 2 or minus Vx by 2. So if you solve that one, you will easily come to this number here. Okay, so I should have drawn it, but I hope you understand that take this Vx and break it into two series sources. The one on the left will be Vx by 2, the one on the right will be minus Vx by 2, and in the middle it will be a ground. You just put a ground there. So now if this creates a small signal negative resistance of minus 2 over Gm, now we attach the LC tank to it with its losses Rp. Now what we are trying to do is we say, okay, if this loss value is Rp, whatever it is, let's say 500 ohms or something like that is a number, then minus 2 over Gm, I want it to be around minus 500 ohms or a little less. I want this resistance to be less because it's negative in value. And when you have two resistances, in parallel, the smaller resistance wins. So this resistance, we want it to be a little smaller than 500 ohms, right? Then what it will do is it will provide the necessary energy. This guy will provide the necessary energy. So if I disturbed it, then this negative resistance will overcome this Rp and help this LC tank oscillate and give you sinusoidal signal, at this point and this point. Okay, they will be 180 degree out of phase, and this is where you're going to start getting your differential oscillator outputs. So that is the basic concept of how we are putting a core to generate a negative resistance and making it oscillate. So what are the different kinds of cores we have that is commonly used? People have all kinds of configurations. I will only show you some of them which are very common. The first one is shown here, which uses a CMOS core. The reason we call CMOS is because we have cross-coupled PMOS and cross-coupled NMOS. Remember, when you're trying to generate GM, if you have a configuration like this, you would get a GM from the P side as well as GM from the N side. So for a single bias current that you provide, you could actually get like GM from both of them, almost like 2 times GM, right? N and P. Here you would only get 1 GM, which is only from the NMOS. So if you had the same bias current here as here you will have less GM, here you will get more GM. So people do this more because then having more GM, you can burn less bias current here, keep the power lower in this core, and still generate the negative resistance based on both the P and N, and make this guy oscillate right here. So this is the CMOS core versus this being the NMOS core, which I showed earlier. And the NMOS core, it will burn more power, and what you can do is you can take the L and split it into 2, and from the center tap you can provide a current source or you can provide a resistor as shown here. You could do all kinds of stuff to actually provide the biasing current and also create the amount of negative resistance that is needed to overcome the losses and make it oscillate. Another difference between CMOS and NMOS is NMOS actually will have less voltage swing, because it's only this. The CMOSs, they are able to cause a much more bigger swing between this, say, positive and negative. This could be cranked down, this could be cranked up higher. So in general, CMOS tends to have lower power and also more swing. But here the problem with CMOS is if your voltage supply is extremely low, right? Let's say you're scaling down this VDD down and down, where you have this voltage drop across this, then you need voltage drop across this PMOS, then you have voltage drop across this NMOS. You might run into headroom issues where this oscillator might not oscillate if you have thing go down quite a bit, your voltage supply. Then you have to use more like an NMOS type core. Otherwise, most people prefer CMOS. If you have the voltage headroom for less bias current, you can get more GM and it just oscillates fine. Okay, so this is some of the simple VCO architectures which you might have already seen, and I'm just trying to kind of repeat them here while going to what all is key, right? When you go into you learn all this in the textbook, but what all else are important which may not be there in those textbooks. So what are the key specifications? Some of the key specifications for the VCO that I could think of is the oscillation frequency, which I'm calling as omega oscillation. So it will oscillate at a certain point, but you can see that you can't tune the inductor. It's an on-chip inductor, but you can tune the capacitor. How? I'll show you. So if you tune the capacitor, you could actually have something called as a tuning range. You could have a range of frequencies called as omega oscillation minimum or omega oscillation maximum. If you could do a very wide range, that's really great, but as I will show you, there are many limitations on how much can you actually tune this guy. Okay, how much can you make this thing tunable? So tuning range also becomes an important thing. So you have the oscillation frequency and the tuning range around it. And the desirable thing is to have a wide tuning range if you can, but there are challenges, trade-offs that go with it. The other key specification, which is what we struggle with most of the time, is phase noise and spurs that come, because of different things that show up on the phase noise. So we'll look at this too. And noise is what we will try to cover first, as you can see from the lectures here, because this is probably the most important thing. And why is this important? So let's step back and see, what is this trying to do? What is this VCO trying to do? It's trying to generate you a frequency. Let's say I wanted 2 gigahertz frequency, okay, from a VCO. You want it to be 2 gigahertz. You want it to be very, very clean. By that means is there shouldn't be any noise. So if this is like a, oh, this is hard to see maybe, but maybe I can still explain through it. So this is a sine wave, right? The solid line, and let's say it's a 2 gigahertz clean sine wave. But once these elements which are there, they will start adding some noise. There will always be some noise added to this system. So even though you're oscillating, you're getting a 2 gigahertz signal, a nice clean sine wave, there is a finite amount of noise that is there, and that noise is going to affect whether you do the zero crossing right here a little bit afterwards or a little bit before. Same thing here. So as you can see, I tried to draw a little bit of dashed type curve. I should really go back and try to see if this, I can bring it back. Okay, I forgot this is the, okay, here. Oh, don't go move, stop. Okay. So this is what I was trying to say. You have a clean sine wave that you have here. And with respect to this sine wave, there is always going to be some noise generated by the circuit. We'll look at what all causes noise, which is shown in the next one. But there is always going to be some uncertainty of when you actually cross the zero, when the sine wave actually start. It's not so sensitive when you go up because your amplitude is so big it doesn't matter. But frequency is from when you do zero crossing to another zero crossing. So there could be uncertainty when you cross these zero crossings. This will have an effect on your frequency, as well as it could also have an effect on your when did you actually cross, right? So at the end we represent that as something which is called phase noise. So phase noise basically gives a number of what is the noise relative to the clean oscillation frequency. That measure is what we call as a phase noise, and we will go and explain this plot. But remember that you have a clean signal of certain amplitude oscillating. Let's say the amplitude is 1 volt, and you want to know how low the noise is. Is it 1 millivolt, 1 microvolt, 1 nanovolt, how low it is compared to this clean signal? That noise, the way to represent that noise is what we do call as phase noise, and the way it is represented is more like this. So I've got the x-axis as the frequency, and your oscillation frequency is, this is the one, this is the clean tone. Okay, now what you want to know is, with respect to the clean tone, you want a relative number. How low is the noise compared to that? So the x-axis at this point, the f oscillation actually becomes more like 0, because we are giving it relative to the oscillation frequency, and we will give it an offset which is with respect to the oscillation frequency. Okay, and the y-axis is called dBc per hertz. dBc because we are giving how low is the noise with respect to the carrier. So let's say if my carrier is 1 volt, I want to know how low is this noise with respect to this 1 volt, and in dB number. That is what is shown here, but then it is also represented per hertz, because what we are giving is, we are not giving the noise. Sometimes it's easier to give like a noise density of the density of the noise, because the noise is not going to be, let's say if you're at 2 gigahertz and you said I went 1 megahertz away from 2 gigahertz, you don't have just noise at 1 megahertz. You're also going to have all the frequencies, right? Why? Noise is everywhere. Like if you look at thermal noise, it's distributed all around. So there is going to be a noise profile, and since it's everywhere, it's better to give a noise density, whose plot will look more like this. This captures all the noise in a density format. So this is noise density, and you said, you know what? I know my VCO is 2 gigahertz. But I'm only interested in the noise up to 1 megahertz. I want to know what is that number up to 1 megahertz. Then what we will do is, you will say, let's say this point was 1 megahertz. You will just integrate the area from lowest frequency that you can measure all the way to 1 megahertz. You will just integrate this whole area, and that will give you the noise in 1 megahertz as a dBc number. Okay, so this value is dBc per hertz. This is giving you the density, and if you wanted what should be the number at a certain bandwidth, you can just take that whole area under this curve and you can integrate, and this will give you the total integrated noise as a dB number. This is dB relative to the carrier. So you have to see, if your carrier is, let's say, 1 volt swing, and you integrated everything to be, say, 80 dB, that means, 1 volt divided by 80 dB, which is how much? 100 microvolt, right? Yeah, so the integrated noise in 1 megahertz will be 100 microvolt. That is how much will come from the active circuitry, which is causing the oscillations but also adding noise. Active circuitry, and maybe from other sources, we'll look at it later. So that is the concept of phase noise, and this basically represents that you want a clean oscillatory signal. You are not going to get it clean. There will be some noise. How much is the noise? This gives you a measure of that. Since we are here, I've got some annotations. I will go ahead and explain it. Most of the time what happens is, in a VCO, the low frequency noise, the region is 1 over f cube. It goes down very sharply with frequency. What it also says that if you are really close, more like at DC type numbers, the value of the noise is going to be very high. So low frequency noise numbers are very high, and they go down as 1 over f cube. Then it's 1 over f square. And eventually it will flatten out to thermal noise. I think we will look at it more. What causes 1 over f cube, 1 over f square? You probably already know, but I think I have a plot again later on to explain that. So we'll look at it at that time. Okay, now this thing looks too big. Let me lower it a little bit. Yeah, maybe a little bit more. Okay. So let's look at what all causes noise. So we talked about it. Noise is going to come, and what effect does it have, and all that. So let's look at this core here. This is the CMOS core with an LC tank in the middle. It has got some current source. You could have a current source on the top. Some people will connect it directly to VDD and have current sources on the bottom. You could do all kinds of stuff. This way, if the VDD was directly here, all its noise will come here. So that's one of the reasons why people will put a current source here to shield some of the VDD noise and all. But let's not go into those details yet. Let's just look at what happens. How does it first oscillate? We'll go to noise, but first let's see how it oscillates, what happens during oscillations, and how noise is added. So I'm going to take the first case where this node is going up. okay, oscillating up, and this is oscillating down. What happens is when that is happening, you would see that this bias current that is there is actually going to flow mostly through this device, because this node is down, so it turns this on. But as this node is going up, this point, this transistor is actually trying to get off. So most of the bias current will not go that way, it will try to go this way. Okay, so the path is going to be more like this, then it's going to flow through the LC tank and then come through here. That is going to be the path for the current. In the case when this signal is going up, when this node is swinging up and this is swinging down. Now remember, this is gradual, this is sinusoidal. It's not a square wave where it went from low to boom high and this got turned on, no. So it goes gradually, and gradually this turns on more and more, this turns off more and more, and this will eventually become the path. And then what will happen is once it reaches the point where it cannot go up anymore, then the cycle switches of the sine wave, right? You were going up and now you're coming down. And during that time, what will happen is you have this one, where you have the current source, it just switches back to the where this guy starts carrying more and more current. This guy carries less current now. It goes through the LC tank and comes over here. So if you look at this, you know, the two cycles, we are adding noise in both the cycles. In the first cycle, we are adding noise from this guy that is showing up here, right, at the output. So these are the outputs. We have to see what is the, who is contributing what. So the first thing to notice is, as I tried to note down here, and most people miss it, is in a VCO structure, we know that these are four, you know, in this case it has got four elements, right, the two NMOSes and two PMOSes. They will always contribute noise. But one of the things that people miss is when it's swinging big time, you know, this is not a single current which splits equally into both sides. Like if you know op amp or something, you have a tail current source, that noise splits equally on both sides and you don't get its noise at the output, right? It becomes like a common mode noise, but that is not true in VCO. As it swings large signal, it actually is not a differential circuit. You can see it's a pseudo differential circuit, and tremendous amount of noise from these tail currents will actually go up through it, and you will actually end up spending a lot of time designing this bias, this tail current and all the other biasing that goes with it, rather than this course. These are simple. You just put four devices which has enough GM for this, and that's, you're done. It oscillates. But the noise will get dominated by all these guys, and that's why I put the current source as the most biggest dominant contributor noise. Not necessarily that every time it will be the most dominant contributor, but it will turn out in most exercises you're going to spend more and more time trying to make the noise from these guys lower. That's why I put it as 1. And also to stress is, this is not a purely differential circuit, it becomes pseudo differential as it's oscillating. So the noise from the current source is very important. Noise from, of course, the PMOS and the NMOS, as you can see from both various cycles, it's coming up here, is there. And of course the LC tank as the other one, because see this, either it's the series loss of the inductor itself, if you assume the Q of the capacitor is very high, or it's the combined tank. You can say that this is going to have some RP impedance in parallel with it, right, based on the combined Q of this, and that will also have an effect on causing noise at the output. So these are the four major contributors of noise which are going to come just from this circuitry, right, and that they will contribute to the phase noise as we talked about, and we'll look at it more, I guess, as we go down below here. Now in this I have not added, but they actually could become very major contributors of noise, which is from VDD supply. Supply could have significant noise. Here we are assuming that to keep things simple, supply is clean, ground is clean, but these guys could pick up a lot of noise from supply and ground, and they could do a lot of damage in the phase noise, you know, even more compared to this if you are not careful in designing it. So as we go forward, you will see that most of the design effort is not to design this core. Designing this core is very simple. But all this biasing circuitry and a lot of the peripheral circuitry, which I don't have included here, the noise from them, how we shield it from the supply, and how do we make it quiet and all that, that becomes the majority of the VCO design exercise. Alright, let's see. So one other thing I try to add here is, normally when you design a VCO, you will also have, you know, you will follow it by some buffers, and in many cases the buffers we use is simple, you know, inverters like that. You know, we tend to use inverter buffers. So it will take the sine wave and square it up. At the end, we are not really using a sine wave. You know, these VCOs will go through some buffers and dividers. It could be divided by 2, divided by 4, or whatever dividers are there. Or even not, if it's not divided by anything and it goes straight away, When you go to the mixer, those are square wave. So these are the buffers which actually help do the sine wave to square wave conversion. And once it is converted to square wave, it's square wave from now on. Okay, so these are the buffers which are there. And I think we talked about this phase noise plot before, but I guess the point that I did not explain earlier is why is it f cube? I don't have all the theory here and all, but you will find a lot of theory, a lot of complicated mathematics, a lot of which even I don't also understand. But what happens is these CMOS devices, right, at low frequencies, this is the low frequency region, the noise is dominated by the flicker noise of these CMOS devices, and maybe even from the current source. If it's a CMOS device there, it will also have its flicker noise. All those 1 over f noise actually gets up converted by f square. So you have 1 over f, it actually gets f converted by f square, so it becomes 1 over f cube. So there is an f square component extra there because that's what mathematics tells us, that it's actually up converting it. Then this region here, which is 1 over f square, is mostly the thermal noise. The thermal noise from all these elements that we talked about, they are not dependent on frequency, right? Its noise density is flat over frequency. That also gets up converted by f square. It becomes 1 over f square. Then we have a region which is 1 over f, which is mainly coming not from this VCO guy, but 1 over f noise of some 1 over f noise might be left of these guys also, right? The buffers. These buffer noises don't get up converted or anything. Only the VCO part gets. So the buffers could have some 1 over f noise, which will have this, and then finally it flattens out because this is the part of the thermal noise of these buffers. These buffers are going to have some finite thermal noise, and that causes this thing to flatten out more, maybe keep going down a little bit, but that's the far away phase noise numbers are really more dominated by these buffers here. So here we go, all the different regions, and you know how the noise profile looks like. So I'm going to pause the video here for a minute, and then we'll pick up again from the next one. Okay, so let's continue on and see from where we left. So as we talked about, oops, going wrong way. So we talked about noise, right? We were talking about this, and we found various kinds of noise, how we represented it and all. And let's see, what does it cause? Is it something that we need to worry about a lot? Or you know, what all does it actually cause? This is again too big. Since I have that, let me just go lower this way. Okay. So the first thing we will talk about is what we call as IPN, integrated phase noise. We mentioned about this briefly when we were going through the RX section. Where you have the clocks, you know, this VCO is generating some clock, and so this is the whole PLL again, and VCO is generating the clock, and the clock after some division or no division, whatever it is, those square waves is going to go to the mixer as a cello, right? And when you receive a frequency there at the mixer to do down conversion, you know that you have a finite amount of noise, and if you take all that noise and integrate it and want to know how much is that noise relative to the actual carrier. Carrier means the clock frequency that we're trying to give it. Let's say this is 2 gigahertz, but then around 2 gigahertz you're going to have a lot of noise, and if you want to integrate all of that and know what that value is, you know, that is what we call as the integrated phase noise number. It gives you a dBc number, that is with respect to the main carrier, how much is the noise. So that is a first area where all this phase noise will go and affect us. So let's look at that IPN first, of what it is, how does it affect. So we looked at the VCO, and we said that, you know, it has some noise profile as we looked at. So this is the phase noise of the VCO, but it's not just the VCO noise that goes to the output of the mixer, right? We have this PLL block, and there are many more components which are going to introduce noise, and the combined noise of that is actually going to go out. the phase frequency detector is going to have its own noise. It will have its low frequency noise. Since these are also CMOS components, it's going to have its own flicker noise and then thermal noise. It will have a profile very kind of similar to this. The difference is here you have 1 over f cube and 1 over f square type pattern. This will not have that. This will just have 1 over f and then flattening out more like a thermal noise. So phase frequency detector will have some noise. Similar profile for charge pump. It's made up of some current sources. They will have similar noises. Loop filter is basically, most of the time we use a passive loop filter, but there also wherever you have a resistor, it will cause its own noise. But what I'm trying to say is all these blocks are also going to have its own noise. On top of that, you have the VCO, their noise, which is another one. And VCO's noise is the only one that we are actually talking about in more detail here. We are not getting into all these other blocks or how this whole PLL system is architected. That itself has its own transfer functions, own sets of optimizations to do. So we are not really going there. We are just trying to focus on the VCO noise, and that's what I will try to only kind of show here. And I will explain this plot. This is a very busy plot, a lot of stuff going on, but I'll try to explain it and then come to this IPN. What is the integrated phase noise and how do we derive from all these things? So let me define the axis first. So this y-axis is dBc per hertz, okay, and this x-axis is frequency. So let's start with this plot, this purple plot, which I have it labeled as open loop VCO phase noise. We looked at the plot previously. We will first start with this plot, okay, and this plot where we have a region of 1 over f cube, then we have a region of 1 over f square, and then sort of 1 over f and flattens out, right? So we will start with that plot, which is this purple plot. This is the phase noise of the VCO. Okay, so I'm just drawing this purple plot here. Now what will happen is, if you look at this this system here, it's not just the VCO or any of these blocks. When you actually cause a noise, right, or you have basically this is a feedback system. If you have a noise injected from this guy into this thing, that will actually get suppressed by the loop gain of this whole loop. If you remember your feedback theory, a system of negative feedback, if you can calculate the loop gain, which is of course a function of frequency, then based on the loop gain it will suppress your noise or also your signal. Like if you have a gain, it will also suppress your gain, all those things that happen with feedback systems. So the same thing here. If VCO did not have this feedback, then the output noise will always look like this. This is the open loop VCO noise. But since we have a feedback, that noise gets suppressed by the loop gain of this loop. Now I have not put in all those equations about the transfer function of this and what is the loop gain and all, but what I can tell you is this is the open loop phase noise of the VCO, and then I have this little dashed, this is supposed to be a red or a pink, somehow after scanning it looks different, so let's just take it as a pink line. Okay, this is what will happen to the VCO noise, which will actually get suppressed by the gain in this loop. That's what the PLL is going to do. So before explaining this, let me also say that this PLL is going to have a finite bandwidth. It doesn't have an infinite bandwidth. Okay, the way we pick up all these components, the charge pump component, the loop filter with the divider ratio and all that, we have a finite loop bandwidth, which is what I've targeted, which is what I'm showing here as marked as loop bandwidth. So let's say the PLL has a loop bandwidth up to this point, which is the closed loop bandwidth of the PLL. Again, it depends on many of the parameters. One of them is the kV of this, but a lot of other parameters which we have not gone, but this is how it looks like. So till its loop bandwidth, right, at lower frequencies where we know that this has got a higher gain, it will actually suppress the VCO noise. So this is like 30 dB because it's 1 over f cube here, and it will suppress, and 60 dB, so it will suppress it even more here. Okay, so it's suppressed significantly. So all the low frequency noise, remember it looked really bad that VCO is the low frequency noise. Ooh, that is very, very high because the 1 over f cube region, right? But that is not what we really worry about so much, because all that is actually handled by the PLL and it actually suppresses it. So this point, when divided by the loop gain that we have at that lower frequencies, it actually gets knocked down way lower. Then as this is coming up, this loop is also losing its gain, the PLL transfer function, it loses its gain. So this is the VCO noise after it is divided by the loop gain. And right around the bandwidth, when this PLL loop is actually losing steam, it does not have enough gain to suppress this VCO noise anymore, then the VCO noise component just becomes same as whatever the open loop is. Because after this loop bandwidth point, VCO noise cannot be suppressed anymore. So you got the same thing coming around here. The purple line and this dashed pink line are kind of the same. So the bottom line here is, if you just look at VCO's noise, low frequencies, VCO's noise is suppressed significantly. High frequencies, which is beyond the loop bandwidth, it cannot, it just becomes the same here. But what happens is overall noise. As I said, VCO is not the only noise contributor. You have noise from phase frequency detector that is also being shaped by this PLL loop transfer function. Charge pump, its noise is also getting suppressed and all that. So if you take all this noise and at the end look at it, this is what it will look like. I'm giving an overall final output without giving you the actual noise profile of this, because going into there will be too many details at this point. But what happens is, at the end, the overall noise profile will look like this. At lower frequencies, it will tend to go up a little more, mainly because the flicker noise from the phase frequency detector and charge pump type components, and all this green line at lower frequencies within the loop bandwidth, the noise is actually dominated by these guys. This reference frequency that comes in, it also has a buffer here, which I have not shown, but that buffers close-in noise, the flicker noise or low frequency noise, that element, plus the phase frequency detector, plus the charge pump, and also from the loop filter. All those components will actually determine your overall noise at lower frequencies, which is this part of the green region. Okay, and then what happens at the low frequencies, the VCO was like almost nothing, because the PLL loop has enough gain to suppress that noise. Okay, so that's what it looks like. But beyond that loop bandwidth point, roughly beyond that, what happens is this green line, which is the overall noise. This is the overall noise here at this point. That becomes almost equal to the VCO's noise, because now the VCO takes over. Why? What happened to the noise of the phase frequency detector and charge pump? They tend to contribute, but their noise will actually go down, and it will, based on how you design it, they tend to be less compared to the VCO. The VCO dominates at these high frequencies. So the overall noise will look like this. Lower frequencies dominated by all these components, phase frequency detector, charge pump and all. High frequency noise dominated by the VCO. And if you then take this green line, and don't worry about disperse, I'll explain that in a little bit. And if you took this green line and integrate all the energy in this green line showed by this shadowed thing, right? That is what we call integrated phase noise. That is the integration of that will give you the total noise as dBc. So that's the total noise with reference to the carrier signal that is there, the clean oscillator that we want. That will come from taking the area under this whole curve. And that number, this IPN, which is the integrated phase noise, in a way also you can take the same thing and convert it to jitter. There are simple formulas to do it, and you convert it back to jitter, which is a time number, a picosecond type number, which is what is used for like ADC design and other kinds of design, where you want to know what is the jitter in the clock, what is the uncertainty in the clock period, or where the zero crossings are happening. So that is kind of in a way related to IPN itself, jitter and IPN. But this is the first consequence of, we have a clock going to the mixer. Mixer doesn't get a clean clock. He also gets noise with it. How much is the noise? This is how we kind of calculate it. And there is a lot of loop dynamics that go on here. What kind of transfer function and everything. But I have not touched on this, maybe in some other lecture, because it tends to get much more detailed than this. It will actually deviate away from the VCO that we are trying to do. So here the high frequency noise is VCO dominated. So that's why when we are designing a VCO, right, when we are designing a VCO, and I will show you how some of the specs are derived, we are more interested in the high frequency part of the VCO's noise, because that tends to fall outside of the loop bandwidth of the PLL, and the PLL cannot suppress it. And this is where the specs tend to be more and more important for the VCO. So we tend to worry more about the high frequency elements of the phase noise of the VCO. So this is one way how that noise affects our system and why it's important. The next way it affects our system is for jammers. So we know that we always have jammers. We talked about it in the RX chain. So let me take a scenario, an example, and then go with that. So let's say we have a scenario like this at the RX input. Okay, I probably need to make it bigger. Yeah, this is better. Okay, so let's say at the signal that is coming in, the RF signal coming in, maybe as an example, let's take this number, say minus 110 dBm. This is the signal, but there is a jammer at some offset. Let's not worry about what that offset is. Could be 1 megahertz, could be less than that, could be more than that. That jammer strength, say for example, is minus 30 dBm. So we are saying that we have an RX, the desired signal, and a jammer, and the jammer is 80 dB stronger. This is actually going to the RX chain, which is basically a LNA and mixer, right? So this thing, the signal and jammer, is actually existing at this input of the LNA and mixer. What is the LNA going to do? Well, LNA is going to take this and simply amplify both of them, and we hope that LNA does not saturate, so we will not worry about the LNA here at this point at all. But let's look at mixer. We have a clock coming in at the mixer, the LO. The LO is actually this signal, right? We are talking about 0 IF type architectures. So the LO is the same as the signal here, the desired signal. So when you down convert it, it will come close to baseband. If they were exactly equal, it will fall right on baseband. But for now, let's just say, these are the same signals. This is where the LO is. So if this is the LO, this shows the phase noise of the mixer LO, right? The LO that's is coming from the VCO, shaped. So this is shaped actually. Yeah, it's not like this. It should be shaped by the PLL. So it would look more like what I showed earlier. It would look more like this green plot, not this purple plot. Okay, so it would be more like this is what will be coming. So that's a mistake on my part. I should have corrected it. Now remember that here if we have certain amount of noise right at the same point as the jammer. So your jammer is here, you have something here, a noise or whatever else, in this case a noise. These two will also down convert to the same baseband, to the same DC value as the signal and the LO will, right? Because it's trying to mix it. It cannot distinguish between which one should I mix down and which one I should not. No, it will mix down both of them. So this point in frequency, so the jammer frequency minus this frequency is 0, which is same as signal frequency minus the LO is 0. So it will down convert this, which is the desired one, but this is the undesired one. So now how much noise can we tolerate here? And that will give us the spec for the phase noise at this frequency. That's how we will derive the specification for phase noise. So let's say one simple way of how it is done. We said that okay, we have a phase noise and all that, but what are these values that needs to be there? How do we derive it? This example will tell you that. Oh, sorry, I forgot to explain this. I mentioned I will, and I forgot. So let me take a minute to explain this before going to the example that we're talking about. So in this green plot, we also said that there are spurs. These spurs come from various sources, For example, you have a reference frequency. So you are going to have certain spurs which are same as the reference frequency. These are called reference spurs. Some of them will be reference spurs or multiples of reference spurs, Some of them can also come because sometimes this thing is I've shown it as a divide by n. This is if it's an integer value, yeah, it's easy. These are called integer PLLs. But sometimes these could be fractional n PLLs, where this n value is say let's say it's not 100, but it's more like, as an example, maybe 100.0025. Excuse me. So you could also have fractional. So whenever you do fractional type PLL implementation, they actually tend to have more spurs. So some of these spurs here could be because this is what we call fractional n spurs, frac n spurs. So you have the reference spurs because of the reference frequency. You have fractional n spurs. You could also have more spurs coming from the supply because, as I will show later on, you could have spurs on the supply just like noise. They will also come and show up here. So all those could cause different spurs. These spurs are not good because why they are not good is this is like noise, and if it increases the noise and you integrate the area, you will also integrate the area within these spurs, whatever the finite bandwidth of the spurs are, and they only increases the noise. So that's why these spurs are not good. Excuse me. Okay, so going back to this example, I got distracted. I forgot to explain that earlier. So what we said is we have the signal and the jammer, and we are going to derive how much of this phase noise number here needs to be so that we can tolerate a signal like this. Because our signal minus LO is getting down converted to baseband, the jammer with this noise value here, whatever the noise strength here, is also getting down converted to baseband. So we need to find the value here. Okay. So assume the signal to jammer is 80 dB here, like that's what we have here. Also, let's say that the SNR needed by the modem is 10 dB. So we know that there is noise here, all those things will be integrated and it will be down converted by the jammer. We don't want that, we want that to be 10 dB lower, so that the modem at least have signal to noise of 10 dB. Not only that, if the modem needs 10 dB, we will like this noise, right, to be lower than other. There are other noise sources. We have talked about noise figure, we have talked about other things which are there. We don't want this to be the major contributor noise. So we're going to put some extra margin on it for this phase noise number to be below other noise sources. What is the margin? 10 dB another. So modem needs 10 dB and I put another 10 dB margin. So all this LO noise that you should have, right, in dBc compared to the carrier should be how much? 80 dB plus 10 dB plus 10 dB. 10 dB is SNR, 10 dB is margin, 80 dB is the signal to jammer strength. So 100 dBc. So the LO you want 100 dBc means compared to your carrier, your noise, integrated noise should be 100 dB below that. So if this number is 100 dBc and we said that let's say the jammer is at 1 megahertz offset, right? Now you want this phase noise as a dBc per hertz number, so you have to find the density. So 100 dBc at 1 megahertz, this 1 megahertz will become 60, so it will be minus 100 minus 60, so the phase noise number in dBc per hertz at 1 megahertz offset will become minus 160 dBc per hertz. That is how, based on a particular jammer scenario, based on the signal, based on how far it is, you can derive the spec for what should be the phase noise number. And similarly, you will repeat this exercise for different jammers for different frequency locations, different standards, and all that will come, and eventually you will come to a unified spec of the VCO where you will say, okay, this is the phase noise, for the VCO. And mostly these numbers are more relevant for far out phase noise numbers, because that's where the PLL cannot suppress VCO noise anymore, and that, see, this green plot is what is showing up as your mixer LO, and all this far out, by far out I mean 100 kilohertz and onwards, because typically let's say in cellular these loop bandwidths are lower. These are like 100 kilohertz, 200 kilohertz type loop bandwidth. So all the numbers above that is dominated by the VCO, and the phase noise of the VCOs become very, very critical. And we have to be able to design it to meet those different jammer scenarios, so that our signal doesn't get corrupted by the noise from the synthesizer itself. So those are the two scenarios where the noise is important, the IPN number, and also when you have specific jammers, the noise is important. Now this is only with respect to the receiver I've talked about. The same VCO can be also used in the transmitter, and there also you have similar requirements, which is, if I go outside of my transmit band, how much noise should I be pumping into the air or into somebody else's frequency band? If you know that number, you will derive it back as what should be your phase noise requirement for the TX there. So that's also another way to derive the phase noise numbers. Okay, the next thing to talk about is the tuning range. This is where we talked about it, and I'll get into more detail of how do you tune it. So again, the same CMOS core, I'm trying to use that as an example. And you have a tunable cap. I said that we have a tunable cap, right? How do we actually implement this tunable cap so that we can oscillate at different frequencies? This tunable cap in general, what we do in the industry is it's broken into two pieces. One is a discrete cap bank. it will be a bank of discrete capacitors, and the other one will be a varactor, which is for continuous tuning. So we have discrete tunable steps and we have continuous tuning, and that's how we implement this this capacitor in general, which is shown here. So as an example, let me just say that this is the discrete cap bank of only 4 branches here. I'm just taking an example of only 4 branches or a 4-bit type of tuning. It could be more, typically there are 7 bits, 8 bits based on how wide do you want to tune it and step size and all those things. But here, this example is just of using 4 branches. So let's start with this branch and say we have 2 capacitors in series with a switch in the middle. Okay, C and C makes it 2C, 2C in series will make it C. So the capacitance of this branch is some C, some unit capacitance C. Then the next one becomes twice of that. So this is binary weighted. So this is going to be some capacitance C. This is 2C, 4C, and 8C. So we have 4 branches where we can control them with 4 bits, and you can have values from C, a capacitance being C, to almost 15C, right? 15C to C roughly. This is binary weighted. Many times people also implement thermometer code where you basically have, if this is this branch, you can copy it over here. You don't have to make it twice. Then it becomes thermometer. So each branch would have the same amount of capacitance rather than doubling it up like in a binary fashion. You can also do that. Many people, based on frequency, step size and all, will also do a combination of binary and thermometer. So there are different ways to do it, but what I'm trying to show here is to kind of help you understand that here you have discrete cap values, and as you have discrete cap values, you will be able to hit discrete frequency points. These discrete cap banks will give you discrete frequency points. Then you have this other one, which is the varactor, and this is the continuous tuning part. We are not interested just in discrete steps. We want to tune every frequency possible, okay, in a continuous way. So first we select the different discrete combinations to bring it close to where we want to be, and then we will apply the varactor, which is tuned by a V-tune voltage. Okay, so its input is a tuning voltage, and with that it will provide a continuous tuning of this within that discrete setting of the frequency that we have. So between discrete steps and continuous tuning, we can cover a pretty wide range of the VCO, and this is how we do tuning. It's not just continuous. You don't put a big varactor there to tune it, because there are reasons for it, and I'll show you that why we don't do it, because the kV will be too high. It will have problems with loop dynamics and all that. But this is how we actually implement the tuning of these oscillators. What I have here is a simple picture showing how we implement the switches. These are normally as NMOS switches. So here is the switch, maybe not one, maybe 2 of them back to back, with source drain here, or the other one could be the source drain here, and they could be in parallel. But what we are trying to do is, if you put two caps here this way, right, the DC here is floating. So this switches, it doesn't know what is the DC value here, it's floating. So what we tend to do is we'll put some big resistors, maybe say 20K, 50K, whatever works for you. When it's turned on, when this switch is on, these resistors will be pulled down. These nodes will be pulled down to ground. These switches will be turned on. So the potential at this point and this point, in a weak fashion, weakly, by this weak devices, will be at ground. So when they're at ground, you get the maximum VGS to turn on the switch, because we want the lowest resistance possible. We want this R-on to be lower. If the R-on is not lower, the Q of this capacitor goes down, because now this capacitor has a series loss with it. We don't want the series loss to be higher. So to keep the Q good, we want a low on resistance. Means we want a big switch. Of course, not too big, because there is a trade-off there, which we'll talk about next. And we also want to increase the VGS. That's why we are defining these at ground with weak or big pull down resistors. When you go off, what you can also do similar is with big resistors, you can pull them up to VDD. So they go off more, because when they go off, we want this off resistance to be high. And not only that, when this cap, this is not going to look like just as a resistor when it's off, it will also have parasitic caps with it. We want those parasitic caps to be smaller, and those caps will be smaller if the switch size was smaller, but unfortunately we wanted a bigger switch size when it's on, so there is a trade-off there. So in one state we want this MOS device to be bigger when it's on, but in off state we want this MOS device to be smaller. Well, you just have to kind of choose, trade it off between those two and see which one works for your tuning range and also your Q when it's on. So this is how we can actually bias these points to pull it down or pull it up based on whether we are on and off. You might also ask that why don't you put the switches on this side, maybe have two switches and the cap in the middle. There the problem is, since this VCO node will be swinging a lot, you don't want the switch resistance to change a lot with the swing. So to keep the switch resistance small, we try to keep it in the middle, because this is a much smaller resistance compared to the impedance of these caps itself. So the switch itself does not see much swing at this point or this point. So if you kept it there, you would see more swing, and it would actually have when the swing was higher, the Q will go down, and you will have this low Q effect, and it will stop oscillating. It will not be able to oscillate, and you'll have to burn more power to do that. So that is the reason why we try to put it in the middle. So now let's go to talking about what are the two trade-offs that we talked about. We talked about Q is important. So to get the Q, you want this R on to be small. You get small R on by making the switch bigger, right? Because as we said, Q is everything. Q, we don't want to lower the Q. If you lower the Q, then it will need more power to overcome the RP. The RP goes lower, and we'll need more and more power, more and more GM to make it oscillate. But what happens when this branch is off? When this branch is totally off, you're not going to see zero capacitance, because you're going to have some parasitic caps here from the switch, right? So like from this point onwards all the way to ground, you will have some here, and if you're swinging differentially, the ground, you can just put them in series. So bottom line is, you're going to see parasitic cap from here to here, which will be much smaller than these caps, but still, since they are in series, between these 2 points you're going to see some capacitance, some parasitic capacitance, which is what we call as the off capacitance. So there will always be some off capacitance. So if I came back to this branch and I says, I'm going to turn all 4 off. If I turned all of these switches off, you would still have a minimum capacitance called C min. It will not be zero, but it will always be a finite capacitance, and actually a significant portion of the capacitance based on how big the switch size is. So there's always going to be C min, and C max is always, of course, the whole thing is turned on. Of course, in C min you will also have to add the varactor, so it will be all these off capacitance plus varactor, that's C min. All this all the on capacitances, right, plus the varactor is C max. So there's a ratio of C max to C min, which is important because that determines the tuning range, right? So even if I turned everything off, there will always be some C min capacitance which will set the highest frequency of oscillation, and C max, when it's turned on, will set low frequency of oscillation. And unfortunately, as you see here, it's 1 to 15. You might think the lowest value is 1, and the highest one, if I turn it on, is 15. So it's C is the lowest value, and when all turned on is 15C, you don't get a ratio of 15 to 1 here, no way. When you actually put it to design, you will be lucky if you can get a ratio of 4 to 1. Yeah, because of this off capacitance of all these switches. So a 4 to 1 value is actually pretty good if you can get it. Now these values are improving as we go to the deeper and deeper, sub-micron technologies, because of lower capacitances with the parasitic capacitance. But still, that is a key term when you design this programmable cap, and that is how the tuning range is affected. How much tuning range can you actually have is there. One thing I also missed to say is, when you have C min, right, another component which is there is the parasitic cap of these devices. So they will also be always there, no matter what you have, even if you have all these 4 branches turned off. So the varactor plus the parasitic cap of actually these cores will determine, and all of that will bring the Cmax to Cmin value to about 4:1. If you can hit 4:1, that's a very good thing, because then your when you do 1 over square root of LC, that ratio becomes 2:1. 2:1 of frequency coverage is really good if you can get it. So this is how we do the discrete cap banks with the varactor. Let's look at the varactor a little more. And actually, let me try to stop here, and then we'll continue with the varactor in just a minute. Okay, so let's continue on with the varactor here, which is, so we looked at the discrete cap banks, how we implement it, right? And then the varactor part. So this is for discrete steps to bring it close to the value you want the VCO to be in, and then you do the final tuning with this, which is the fine tuning. So this is an analog tuning part of it. So let's look at a varactor. The varactors are typically more like a MOS device, which is I'm showing an accumulation mode NMOS varactor. So this is an NMOS device. So normally, if you have an NMOS device, you will have it N plus and N plus in a P substrate. But you can see that this is put in an N well. Why? Because if you put it in N well, this channel is always on, right? So this channel is always on, and it's always accumulated of electrons. So this is called as an accumulation. This is the example of an accumulation mode. And what you do is you take the source and drain, and you short it, and you make it one terminal. So this is one terminal of the capacitance. The gate is the other terminal of the capacitance. So this is one terminal, this is the other terminal of the capacitance. And let's see how this forms a varactor. So if this is always on, then what will happen is, what is the capacitance if this channel is always there? You want to see the capacitance from gate to source and drain are shorted together. So remember, there is always some little teeny tiny overlap capacitance, right? Which we call as like, I think I will label as CGDO and CGSO. I think those are kind of the names. So CGSO is the gate to source capacitance, overlap. CGDO is the gate to drain capacitance overlap. So that's always there, whether the channel is on or off. But when the channel is completely on like this, you are going to see the full capacitance, which will be, the whole oxide capacitance of this. So you have a COX, you have a W and L of this device. So the total capacitance, COX, which is the density of this oxide, multiplied by W and L, will give you the total capacitance, plus you will add CGSO and CGDO. That is the value of the capacitance you will see if this was completely accumulated of carriers, right? Which is how it is right now. That is what will give you the Cmax value, which is the complete CGS when it's on. So that is actually approximately COX times W times L, okay, plus CGSO plus CGDO. I guess I just put the CGD there, but it's both of them are there. Both the overlaps are there, right? So that gives you the max value. Now let's look at it that somehow we changed the biasing voltage across it. We kept it constant, and we changed the voltage in the gate in such a way that we actually go to the Cmin. Cmin is where the channel is completely depleted of carriers. Okay, if the channel has absolutely no carriers left, then this channel is off. There is no channel, right? You have an N well here, but this becomes more like a P-type region right near the channel, right? Because it's now accumulated of holes. The electrons are depleted in this case. So the only capacitance you would see is CGSO and CGDO. That is the minimum value. Okay, so as you vary the voltage, and again, if I have to go with this plot, first of all, see what will actually completely deplete this channel of electrons. So if I had the source and drain fixed at a voltage, and since it's an NMOS, I have to apply. If I increase the gate compared to source and drain, right? If I increase this voltage, this will only bring in more electrons here. So we don't want to increase the voltage. We have to actually decrease the voltage. So if I made the gate more and more negative compared to the source and drain, so if the gate went down, okay, it went more and more negative relative to source and drain, then we will have more and more holes that will appear here, and it will deplete, and that will be the condition for C min. So in this plot, I guess to be consistent with this plot, what you have to say is gate is fixed and the drain is being moving. Okay, so the gate voltage is kept fixed and the drain voltage was actually more like, negative compared to the gate. Then this is heavily turned on and we're going to get C max. But if you kept the gate the same voltage, whatever voltage it was, and you moved the drain to be more and more positive, right? So the drain, source and drain value became more and more positive. Then your VGD, gate to drain or gate to source, became negative. That means now you have depleted this channel of electrons and you have actually generated more and more holes, and your capacitance has gone down to CGDO and CGSO. So this capacitance movement will happen something like this. This is the plot. This is called the CV plot. What is the capacitance seen between these two nodes when, for this plot, the gate is fixed and the drain is being swept from a negative value to a positive value. It's really negative with reference to this. It's not an absolute negative value. Okay, so it's always relative. I'm talking about relative. This voltage relative to whatever this voltage is. We'll get a CV plot like that, and as you're able to get, you could have all this different continuous voltage. For that you will have continuous change in capacitance also. That is what we do in a varactor, and this is an accumulation mode varactor. There are depletion mode varactors also where it works opposite, which is this will not be an N well, this will be a P well, where normally it's depleted and you will actually turn on the channel to get it. So there the curve is similar, it will just be opposite, flipped to get the depletion type varactor there. Okay, so let's see how do we normally typically implement. So we'll take one of these varactors and we will put them back to back. For example, maybe in this case, as I'm trying to show as an example, you have the source and drain of this device back to back to source and drain of the other device. These two terminals are A and B. These are the ones which are connected to the main cap bank, which is here. This is A and B. I guess I don't have A and B here, but think of it as A and B here. This is where the inductor is, all this cap is, and the varactor. It's not one cap, it's actually two caps in series back to back. And in the middle you're putting a V-tune voltage. So this particular arrangement would be something like this, where you have one accumulation mode varactor in its own well. The potential of the well is same as this, and that would actually help you generate a plot like this. So you have your capacitance will change. There are two of them in series, and as you change the V-tune, the capacitance is changing, right, as based on the CV plot. Based on what is this V-tune? This V-tune voltage is also relative to what is the DC voltage here at A. The DC voltage at A is same as in B, right, the DC value, and with respect to that you have the V-tune here that you're changing, and based on that you will see a CV plot like that. And once the capacitance changes at the end, what you really get is a plot like this, where the x-axis is the V-tune value. Okay, the V-tune which comes from, so where does this V-tune come from? I think I need to take you back. Okay, so the V-tune comes from this loop filter. That is, if it's a passive, it's from the charge pump, and this charge pump runs out of some VDD and ground. Okay, so it has a VDD and ground, so there is a bound to what the V-tune value could be. V-tune value could be all the way to ground, or V-tune value could be all the way to VDD. Those are the extreme bounds, which are the bounds which are shown here, 0 and VDD. So if you swept your V-tune here and you looked at the oscillation frequency of oscillation, it would be more like this. It would be almost like a linear type thing you would see here, but that towards the end it will saturate. And the reason it saturates is because your C is saturated here, right? For one end of it, it will be saturated to C max, the other end it will be C min. And because the saturation points, you have the frequency is also saturated on both sides. And there is a usable range that we use for V-tune. So the range of V-tune cannot be from 0 to VDD. It is less than that, and that is what we call as the usable range, where the frequency is sort of almost linear, with V-tune. So here is the output frequency, here is the input, which is V-tune, this is the usable range, and you get this kind of a characteristic. Now one other point of the usable range is normally what happens is, if I go back and I said, right, V-tune is coming from the charge pump followed by a passive loop filter. So the charge pump is built up of current sources. If you want current sources to work properly, then one of the rule of thumbs we say is we want to maintain about 200 millivolts of VDS drop across current sources. Okay, so this could be almost 200 millivolts or maybe a little more from ground. So if your V-tune, the lower range of V-tune was at 200 millivolts or 300 millivolts, that's a good number. Nobody will really question you, because if you made it even lower, you will be putting unnecessary pressure on the charge pump block, which will not act as a good charge pump current. It will not be able to give you the charge pump current, and once you don't have that, the loop dynamics of the PLL, the negative feedback system, and all the analysis that you're doing, many of the non-idealities come here. That won't be true exactly. So for the charge pump currents to work properly, keep it to be like 200 millivolts or a little more. Okay, so that becomes the lower end of this usable range of V-tune. Same thing at the upper end, same thing. If you kept 200 millivolts here, keep it 200 millivolts less than VDD. So that the charge pump, again, so the charge pump is comprised of mainly two current sources, one on the top, one on the bottom. Okay, so those are like two current sources on series, and we are taking the middle point. So there is a current NMOS current source on the bottom, which you don't want to squeeze. So you want to give enough VDS to the NMOS current source here. This is for the PMOS current source, where you don't want to squeeze the PMOS current source, so you are giving it the room. That determines the usable range of this V-tune. So that's there. So this is the varactor part and V-tune, and continuing with it, as I said, is, we said that the VCO, its input is voltage, its output is frequency. So there is a voltage to frequency conversion that is happening here, and that's why the name voltage control oscillator. And it has a term that is used very frequently in all the PLL loop dynamics and everything. It's called kV. kV is the derivative of output frequency to input voltage. So this is the transfer function. The transfer function of this VCO is given by kV, which comes out to be some XX megahertz per volt. Typically, what do you want this kV number to be? Maybe somewhere around 50 megahertz per volt is a typical number that is used in many applications, maybe a little more or less, but you don't want this kV number to be very high, because a high kV could cause problems in PLL loop dynamics of, just trying to give you some numbers of this. So the transfer function of this VCO from voltage to frequency is kV, which is given this way, the derivative of the output frequency to the input voltage. So how does it look like? As we said, same plot as we drew here. I'm just going to draw the plot again here. And we said this is the frequency of oscillation, this is the tuning voltage, going from 0 to VDD, but only having a usable range for V-tune. In that it's linear, after that it kind of saturates. So if you take a derivative of this, this is the output, this is the input. The derivative will give you kV, which is the transfer function of VCO. That plot will look more like this. So you have the same V-tune, and with V-tune, somewhere in the middle, you would get the maximum kV. Then as it saturates, its kV will actually go down. So the transfer function actually changes. This VCO does not have a fixed transfer function. This kV is not fixed. It changes over where your V-tune value is. So you have a kV max and a kV minimum. What you don't want is, you don't want this kV max and kV min to be too off, too much different. For example, let's say if this is 50 megahertz per volt, that is 10 megahertz per volt. That's a 5:1 ratio. That's kind of a big ratio. What you would like is to be maybe keep it within 2:1 ratio. Again, why? Because if the kV variation is too much, and you go back to your PLL loop transfer function where kV is there, any change in kV could cause potential instability problems, or could cause the loop to be less stable. I mean, not less stable, slow. Your loop bandwidth might go down and the PLL might become slower and all those things. So there are stability problems that could come. There are speed problems that could happen. So since it's a transfer function of a block, ideally we want this to be constant over VTune, but you have to keep in mind it varies, and you have to know how much it varies, and these are the things you have to take care of in design, both design as well as system level calculations that you're doing for the PLL loop dynamics, its transfer function, its stability, and all those things. So that is KV. Now, an extension of this that you also need to keep in mind is, remember that if you go back in the structure here, right, you are applying a VTune, you're seeing how the frequency changing, you're deriving KV and all that. But that is true for a particular setting of this discrete cap bank. Okay, so you could have the cap bank set to all zeros. If you have all zeros, you will be at the maximum frequency. If you have all ones, right, all of them turned as 1, means all of them on, you will have the minimum frequency. So this KV characteristic is actually also could be more like this. This shows the KV max and min for a particular setting of the discrete cap bank. But you could have a case like this where this is the maximum frequency where all the cap banks in the discrete are off. You have a maximum frequency, and this could be a KV plot for that. Again, KV max and min for that particular maximum frequency setting. Or you could say I'm going to turn on all the cap banks, maximum capacitance C max, and I'm going to derive the KV. So this could be at the minimum oscillation frequency. This is also something you have to keep in mind when you're doing your system level analysis. Is the loop stable? Is the loop fast enough, or is the loop slow enough? Those kind of things. PLL loop dynamics, when you do that, you will have to also keep this KV variation. So KV variation is there. There are ways, people have come up with different ways to reduce the KV variation. Because again, the desirable is if KV does not vary, that's good. You know, it's almost like saying the VCO has a fixed transfer function irrespective of, you know, the tuning voltage, and also irrespective of the discrete cap bank tuning, right, that we do. So that has to do with KV as the transfer function. Now let me also touch a little bit back on what we have talked about, but also kind of add a few more things to it. So on frequency coverage. So, you know, we talked about it. In this example, we have discrete cap banks. Sometimes this discrete cap bank is also called as coarse tune cap bank. Why is it called coarse tune? Because remember, you're trying to set the VCO to a particular frequency. You can go through a set of coarse tuning steps and bring the VCO close to what its frequency is, right? By doing this, by selecting the right digital code to give an approximate discrete value of a capacitance, which will bring you closer. It's not exact, but it will bring you closer to where you want to be. That's why it's called as a coarse tuning. So discrete and coarse tuning, sometimes also referred to as the coarse tune or CT bank. This varactor part is the fine tuning, and as we showed, as you apply VTune, this will fine tune the frequency in a more analog way, so you can come exactly close to where you want to be. So we have a CT bank and a fine tuning bank, also called as a FT bank. Now here is a set of important set of plots that we generate after you put the whole VCO together and you simulate it and you see the frequency coverage. Am I able to hit all the frequencies or not? All that stuff. So let me explain what this plot is on the x-axis. On the x-axis is basically VTune, and I say VTune, this point is VTune minimum and VTune maximum. I am only showing the usable range of VTune that we talked about. So VTune minimum is not 0. This could be around 200 millivolts as we talked about, so we don't pressure the NMOS current source and the charge pump. VTune max is also 200 millivolts or something like that off of VDD. So I'm only showing the usable tuning range here. So within the usable tuning range, what I want to do is, as we sweep VTune, I know I'm going to get a frequency curve. So let's start with the lowest curve here. This is the curve when all the bits, since we have 4 bits, four digital banks here, right? So we talked about 4 digital banks. That means these 4 banks are controlled by 4 bits. If we set all of them to 1, which will give you the maximum capacitance, you will get the lowest frequency, which plot is here. this first line here, the lowest, is when all those cap banks of the CT cap bank, they are 1, means they're turned on. So that will have a plot like this. Then if I turn the LSB off and I say, you know what, all of them are on, but I'm going to turn this LSB off. So it will reduce the capacitance a little bit, so it will increase the frequency, and you will have this second plot. And the step size is what we call as the LSB step size of this cap bank. This is important because you have to see, and we'll come in just a minute to why is it important. So we went from the maximum capacitance to 1 LSB less. This is the LSB step size and the frequency that you got. Then if you reduce one more LSB, you will come to this plot, right? Then one more LSB, you will come to this plot. So this way, you can generate a total of 16 plots. Since we have 16 combinations possible, the highest one is for C min, where the whole bank is off. And all you are seeing is all the parasitic caps that are left there, right? So this is the maximum frequency. This is the minimum frequency. And towards the lower end, this is your LSB step size. This and the LSB step size, the higher end, most of the time, it will not be directly same if you just use these values, because there is an effect of C min that comes in, which is not captured here. So you'll actually have to tweak these values a little bit to get this step size, if you wanted this LSB step size to be same as this. Or in other words, the LSB step size or delta F increasing for each of these codes, if you wanted it the same, you will have to tweak these capacitances a little bit. They're not going to work as it is shown here. Why? Mainly because, as I said, we are not capturing the effect of C min here. The minimum capacitance or the off capacitance, we are not capturing that. So to keep this LSB step size the same, need some tweaking here. Okay, now that's one thing. The other thing that is very important is, remember, we are trying to come to a particular frequency. We are trying to lock this guy. It may not be 2 gigahertz, it may be 2.0135987 gigahertz, you know, some value which the PLL is capable of locking. Okay, so to lock at any frequency, what we are doing, first of all, we are saying we are going to come close to that frequency by going through these discrete steps, right? And once we have come close by, then we want to exercise this fine tuning to bring it exactly dot on where the frequency should be. What that means is, if I said that I have this frequency here, okay, that is what I finally want to lock into. You can see I can do it in many different ways. I could start, at least in this example, if I draw a straight line, this dotted line, I could start with this, which is the code where all bits are 1, and I will need a V-tune which is close to the maximum value. That's one way I can come to this, lock to this frequency. The other one could be, so this is all ones, right? 1 1 1 1. This is 1 1 1 0, 1 LSB less. I could apply that code and also have a V-tune close to whatever the V-tune value here is. I can also lock there for this digital code for the CT bank and this value of V-tune. I could also lock by saying the digital code is 1100. Is it 1100? No. It's so this was 15, 111. This is 14. This is 13. This is the code 13. Okay, so if I had code 13, I could lock with a V-tune value of whatever this is here, right? Then code 12, I could do this for a V-tune, and similarly, you can go all the way up, and you can, you know, show whatever the plot here was. For that, I could do it. So the key point here is there are many solutions, right? For every code, you have a certain amount of V-tune. What you want to do at the end, the point I'm trying to make is, you do not want to have a case where there is only one solution. Here there are like 4 or 5 solutions, right? You could have 4 or 5 different digital codes, and for each code there is a V-tune value for which you can lock. You want to have that. Imagine if these plots were in a way where they were like more flat, right? So this has this slope, right? But if it was almost flat, where you had only one digital code, and that was the only code which intersected this frequency point, and you didn't have any digital code, that is a dangerous situation, because what if you couldn't get to that code for some reason? Then you will just not be able to lock. So the bottom line is you want many codes, at least 3 or more codes, 3 or more of these lines, each line being one of the digital CT code, right? You want at least 3 or more codes to intersect that frequency point for the usable range of V-tune. That guarantees you that you will always lock to every frequency. That's why if you're a VCO designer doing this thing, you will do this exercise. You will generate these plots of frequency with V-tune for every CT code, and you will make sure the LSB steps are uniform. They are not too big of a jump or too small of a jump. That's the first thing. The second thing is you will have at least 3 or more codes where you can lock to any frequency. You want to ensure that, to make sure that it's a very robust design of a VCO. Excuse me. Now this thing will kind of clear up more of why we want this, because it has to do with something we call VCO calibration. So VCO calibration is a step that happens, I think, in most of the products which are there in cellular, if and all this stuff. When you wake up, the digital knows that I want to lock to this channel, and so when you wake up the chip, first when you power up all the blocks, right, even before all the blocks have settled and all, in case of the VCO, what you will do is you will just not turn it on and start this. So what I mean is, in the beginning, I need to go back to this loop. Okay, so let's say first the chip was off, the power was down, and suddenly you power up the chip. When the power of the chip comes, you have a reference frequency which is there, but you don't turn this whole loop on and tell them, hey, scramble around, figure out how are you going to lock to this frequency. I'm going to give you the right digital code. For this code, I want this frequency, just figure it out. Here is the N value and figure it out. No, you don't do that. That will get this loop going crazy. It'll take longer, it may not lock, all kinds of problems could happen. What we do is, first, when the power up has happened, even before you exercise these blocks, like phase frequency detector, it's turned off, charge pump is turned off, loop filter, it's a passive one, but it's turned off, it's cut, it's not even in a loop. This whole loop is cut. You put the VCO in an open loop and you're going to calibrate the VCO. What is the purpose of this calibration? The purpose of this calibration is to bring the VCO close to the frequency that you want. So you will calibrate the VCO open loop and try to bring it very close to where you want in discrete steps. And once it is there, right, then you will let this loop close, because you have taken 90% burden off of this loop. This loop has less pressure now, and you have already brought it closer to what the output value should be, output frequency. Now you're telling the loop that, hey, go ahead and finish the rest 10% of the job and lock me exactly to the final frequency you want. Then the loop will go around and give you the right V-tune to give you the final one. So that's how we do it. So we don't put complete pressure on these blocks. We first calibrate it, bring it close to it. While this loop is broken, these blocks are kept off, and then these blocks are turned on and told, settle down to the final V-tune value, so I get the final frequency that I'm looking for. So now the process is called VCO calibration, and what we do in VCO calibration is as I said, we will keep the loop broken, and we have the VCO whose output is the oscillation frequency. Remember, it has got two inputs. It has the 4-bit CT code and it has a V-tune. Okay, this V-tune is not coming from the PLL loop right now. We will actually fix the V-tune to a fixed value, which in this case is VDD by 2. Remember, the V-tune has a usable range, but we really want it to be in the middle of this usable range. So we lock it to VDD by 2, which is the half value, so we'll fix it. Okay, we'll break the PLL loop and we'll fix it at VDD by 2. Then we'll apply the middle of the CT bank code. The middle in this case is 1000. So when you give a CT bank code, when you give it a V-tune or VDD by 2, this guy is going to start oscillating, right? It's turned on, it'll oscillate at some frequency. We don't know what it is. What we do is we take that frequency and we have some counters. Let's say simple digital counters. Excuse me, not digital counters. They are actually, the first set of counters are actually high frequency counters, and then we have digital counters. But basically you're trying to do it counting. Let's say this value is 1000. Okay, let's say the desired frequency I want, as an example, is 2 gigahertz from here. That 2 gigahertz is probably not going to come if I initially set this as 600 VDD by 2 and 1000, right? This is some frequency, but I want it to be 2 gigahertz. Let's say whatever that frequency is divided by m. Let's say it's 1000. Then I put it to a digital block which has this crystal frequency to it. So this is a very accurate frequency. Okay, and what this digital block is trying to do is it's trying to count pulses. So as an example, let's say it's trying to count pulses in 1 millisecond. It's clocked by this guy, and this it's trying to see how many clocks did I count in, say, 1 millisecond. So let's say if this was 2 gigahertz exactly. Okay, let's assume this was 2 gigahertz. 2 gigahertz divided by 1000 is 2 megahertz. So if you put a 2 megahertz clock here and you told it to count something in, say, 1 millisecond, how many pulses will it count? It will count 2000 pulses, right? 2 gigahertz, 2 megahertz, in 1 millisecond it's counting 2000 pulses. So that is what the digital wants to do. Let's say we put 100, and rather than 2000 pulses, it counted something like, say 900 pulses. That's 1000 pulses. It counted less. So what the digital knows that, oops, this is not 2 gigahertz, it's way less than that. I'm counting less pulses means this clock is not fast enough, it's slow, so I need to make it faster. How will it make it faster? It will come and change this code from 8, this code is 8, right? Yeah, 8 to, it wants to make a code where it will actually make it go faster, right? So it will like to have a code of, say, 4. So from 8 it will go in a binary fashion and go to a code 4, because if it is that then the capacitance is less, that means the frequency will increase. Let's say when it did the code 4 and it counted it again, now it says, oops, rather than counting 2000 pulses, now I counted more pulses, say 2500 or something like that. Then it knows that, oops, this is not 2 gigahertz, it's actually running faster than 2 gigahertz. So I know that when I'm 8, it's going slow. When I'm at 4, it's going fast. It's a code between 8 and 4. So what's a code between 8 and 4? It will next go to 6. It will make it 6. Okay, so it will be 0, 1, 1, 0. So it will go to the code 6. So for 6, it will see it, and now it will check it again. And it will say, okay, what do I get? Am I going faster? Am I counting more pulses or less pulses? Let's say it counted more pulses. So it says, oops, it's still fast enough. So now I know that when it's 8, it's slow. When it's 6, it's fast. So it has to be the code 5. So it will change it to code 5. And by code 5, it has actually brought it closer to 2 gigahertz. It's not 2 gigahertz. It could be a little more than 2 gigahertz. It could be a little less than 2 gigahertz. I don't know what it is, but it knows that it's somewhere closer there. And hopefully it's one of these plots here, which is closer to VTune in the middle, because we kept the VTune middle here, VDD by 2. And so once you have a code of 5, now what it will do is it will set the CT code as 5, and then it will enable the whole PLL loop. It will turn on the divide by n, it will turn on the phase frequency detector, charge pump and all, and then it will generate the correct VTune. So remember, the VTune was sitting at VDD by 2. It will start from VDD by 2 and it will correct itself either up or down a little bit to bring it closer to 2 gigahertz. So this is what is very important of the VCO calibration that we do in the beginning when the chip powers up, and we help it find an approximate solution by providing it a good approximate solution for the CT code. And afterwards we allow the whole PLL loop to come on and let it lock to the VTune value such that the VTune is actually closer to the usable range. We don't want to go towards these extreme ranges, right? We want it closer here, and that is the reason why we start from middle of the range, bring it closer, and then let it deviate a little bit here or there based on which is the frequency code and what is the corresponding VTune it finds to lock to that. So this is the process of the VCO calibration, which I hope now you get a good picture of how this VCO is. It's an LC VCO, but how we are making it tunable, how we are calibrating it, how we are bringing it close to its final value, and then we are closing the loop so that we can settle fast without too much of oscillations and problems and all that stuff. Okay, let's continue on something else I think I touched on briefly, but now I'm going to go back to noise. So all this section was on the tuning of it, the discrete tuning and the continuous tuning, and now we are going back to noise to look at noise, some more of the noise and some more of the aspects of the designing of the VCO. Supply sensitivity. So VCO, as we said, is its input is V-tune, its output is an oscillator frequency. This transfer function we call kV. But this VCO is also very, very sensitive to supply, and supply is never clean. It's always noisy. Okay, so there is a sensitivity from supply, which is say kVDD, to the oscillator frequency. That is also what we call as kVDD. This is from the VDD to the oscillator frequency. This value, ideally, you want it to be 0 or as low as possible. If it's low, that tells that this oscillation frequency is not going to be affected by noise and spurs and other junk on the supply. It will mainly be dependent on V-tune, which is what we want. We want this oscillator to react to V-tune. We don't want it to be reacting to VDD, to noise. That will not be good. So, but unfortunately, the supply could look like this. The supply will have noise. The supply could come from an off-chip pin, like this could go to a pin. If your VCO is running out of a pin, you have a supply pin, and it could be supplied by a power management chip. There also you're going to have noise, and power management chips will have spurs. They are really, really nasty spurs which is generated from the power management chip. So this is what the supply could look like. It has a DC value, and this is frequency, and over frequency it will have a noise profile which could look like that. So this could be the noise coming from external, or it could be the noise internal. These chips not only have VCOs, they have all the blocks in there. Like a transmitter could be pumping a lot of power, and that transmit output noise could be coupling in terms of noise and spur. There could be other clocks like the reference clock running. There could be noise from there. So there is a lot of coupling that could happen on chip itself, and it's in today's world it's a challenge to keep these supplies clean, or to reduce coupling. Coupling is a big concern in making these chips work in today's world. So supply is dirty. What will happen is the VCO actually amplifies this thing, as I will show later on. It will all show up in the phase noise. So VCO has a phase noise which probably looked like this, but now it looks like that. All the spurs will come up, and I think we looked at it earlier also when we were talking about IPN, integrated phase noise, how all these spurs come up. So from the supply also it could couple, and we don't want it because this is actually increasing the noise, and we want a clean oscillator, but this is not helping us get a clean oscillator. It's making the oscillator more and more dirty. So there could be significant amount of noise coupling that could happen from supply to the VCO phase noise as spurs, and we want to reduce it. And one of the things people do is they would build LDOs. So we normally don't drive a VCO directly out of something. We will have a local regulator, a low dropout regulator, which will try to shield a lot of this supply type of junk from getting to the output. This, we expect it to have good PSRR, so it can suppress a lot of this noise and spur there, and then make the supply more cleaner going to the VCO, so it is less sensitive to all this junk that is out there. But when you do that, watch out for noise again. And why I say that is, whenever you put an active block, it has its own noise. It's suppressing the other junk noise from outside, but it itself is generating noise, and that noise could become quite significant for the VCO. And that is where you have to look at reducing that noise there. So here's a simple diagram I put in there to show what a simple system like this might look like, which is, here is our VCO core, the CMOS core with LC in it and a bias current source here. But everything before that is all this biasing. So how this biasing works? Well, let's say you have a band gap circuitry that's generating a band gap voltage. This is like a voltage reference, a more accurate voltage reference for the circuitry. Band gap will also have a lot of noise. You need to filter it, so that's why you have a big low pass filter here to filter this guy, the noise, so that the band gap noise does not come here. So this is providing a VREF, and hopefully this VREF has a lot of the high frequency noise filtered out by this guy. So So of course when you put it, this resistance will also start contributing to noise, because the resistance thermal noise will also come at Vref. You cannot avoid it, so don't make it too big. You know, we pay a penalty of keeping the resistors, you know, acceptable while increasing the cap, but a lot of cap on chip means you have area you have to burn. So anyway, so hopefully not so noisy Vref that has come here. Then you put an op amp and this kind of a configuration, say R1, R2, if they are in feedback like that, then the output voltage becomes 1 plus R1 over R2 times Vref. Okay, so this becomes the output voltage or the VDD of the VCO, right? And this op amp will actually be connected to the VDD, which I have not shown here, but that's where all the noise will be. But when the noise comes to the op amp, then you have to make sure that it has got enough PSRR to suppress all the junk from the power supply from coming in here. That is what will try to clean it up, the junk from the VDD coming to this VREF. But let's say even if it didn't have any junk on the VDD, what has all this done? Putting all this, okay, is to suppress anything from VDD. But if VDD was clean, this guy has its own thermal noise, right? There are some resistors and all, they will also generate noise. All that comes here, and as it goes through this guy actually amplifies it. If this point is coming from some current mirror again, and more like an AC ground type thing, then this has amplified all that noise. So you have to actually design all these blocks to be super low noise to maintain the kind of the phase noise numbers that you're trying to do. It would have been nice to have a clean supply here, but unfortunately, since we don't have a clean supply, we are putting all these blocks to filter the noise from the supply. But these blocks themselves start adding a lot of noise, which gets amplified through here and shows up significantly in the phase noise. So you will actually end up designing these blocks more than the VCO. As I mentioned earlier, the VCO core is a simple core, and you just put it in and it oscillates. That's fine, but that's not the end of the story. All this biasing circuitry and everything else that goes around, that is where 90% of the effort goes on to make sure that their noise is lower. They provide enough PSRR to supply any junk from the supply, and after you have done all that, then you say, okay, now my VCO is ready, even though you have probably spent 10-20% of your time in just actually designing the core and the rest of the time in designing all this peripheral circuitry. Okay, let's end this thing with some trade-offs, which I think you probably have figured out by now, but let me also say some of this that I think would be useful to say is, so in this LC design, you know the size of the inductor, and somebody might ask you is, when you're doing this design, would you like this inductor to be small, or would you like this inductor to be big, if you were to pick? So let's say if you could pick the inductor to be big, that's actually a good thing, because a bigger inductor means it'll have a bigger RP, right? Bigger RP means losses are less, which means the amount of power we have to burn in this core, I bias them to get the right GM, right, to overcome this RP, is actually lower. So for low power designs, if you're talking about low power, right, where you want to control the power, you should try to go for as big of an inductor as possible. But if the inductor gets bigger, that means to oscillate at a higher frequency, right, you have a certain C. 1 over square root of LC is the oscillation frequency. So now it puts pressure. So if inductor is higher, C is lower. That means the C could come closer to C min. Just remember, you have a cap bank, and when it's off, it still has some minimum capacitance, off capacitance. So having a small capacitance is not necessarily good, because that puts pressure on your tuning range. So you might be able to get lower power, but now you don't have much tuning range, much range to move the C capacitance, and thus you end up with a lower tuning range. So those are the trade-offs there of going with a small inductor or going with a large inductor, okay, in terms of power and tuning range and all these things. And the other point I mentioned, it's not a trade-off, but I think I just wanted to mention this, is the design of the VCO core itself is a small part of the overall effort. You will probably spend 10-20% of your time just doing that, but the rest of the time is really spent on all the peripheral things like current biases, voltage biases, filter here and there, LDOs, this, that, all those things. That is what you have to put it together. And as a VCO designer, you have to do all this together. You cannot just say, oh, I'm just going to do the VCO and somebody is going to do these blocks for me. No. You should really design all of it together so you have a good understanding and a grasp on what block is causing what, and then simulate the whole thing So when you simulate for phase noise, don't just simulate the VCO core, you need to simulate the whole thing. So you know that this is that final noise that is coming, and it includes the contribution from all these biasing circuitries and everything, and we are good and we are meeting the specifications. So a lot of the effort will actually go in designing these other blocks rather than the VCO itself, but that completes a complete VCO design exercise, and it's not complete if all these things are not put together as one, a complete picture. You have to have everything in there and not just the core. So hopefully through this lecture now you have more insight into how we take the VCOs, which are their simple traditional LC type VCOs, and what are the different things you go through, steps to learn and to make sure that it achieves what we are trying to do. Thank you all.